Hello, this is Miss Valdez, and in this video I'm going to work through the 2.5 through 2.8 practice test. So this first problem has to deal with graphing a parabola, and the first thing we're going to do with this quadratic here is rewrite it in vertex form. So I'm going to do y equals, and I'm going to take out the -3, that's the a value. So if I factor out that -3, and then I'm going to leave something, and we're going to push that +7 to the end. And now I actually also have to add that same something to the other side of the equation. So to figure out what goes in that box there, you have to take -b, divide it by 2, and square it. So in this problem, our b value is this -4, so it's going to be +4 divided by 2 squared, which gives you 4. So that means I have to put 4 right here to complete the square. Now, notice I didn't actually multiply or add 4 to that side. Since I have this -3 times 4, I actually added a -12 to that side. Okay, so now I have this equation, y minus 12 equals -3, and then I'm going to go ahead and factor this because this part in the parentheses is now a perfect square trinomial, which I can factor as x minus 2 squared. Because the two numbers that multiply to 4 and add up to -4 are -2 and -2. All right, and then I still have this +7 at the end. Now I want to get y by itself, so I'm going to add 12 to both sides. So these cancel, and I'm just going to write this in function notation. So f of x is equal to -3 x minus 2 squared, and then 7 plus 12 gives me +19. So this would be the same function in vertex form. So there's two ways we could do part B here. Since we already found vertex form, you can probably just see that the vertex is 2, 19. But if you didn't know that or you weren't sure, you could still do that other process where we find the x coordinate by taking the opposite of b and dividing it by 2a on this original function up here where a is -3, b is 12, and c is 7. So if we do that, the opposite of b is -12 over 2 times a is -3. So -12 divided by -6 is 2. So now to get our y coordinate, we can just plug back into the original equation. Everywhere we see x, we're going to plug in 2. So we have -3 times 2 squared plus 12 times 2 plus 7. So that's going to give you -3 times 2 squared is -3 times 4, which is -12 plus 24 plus 7. And that all adds up to 19. So your vertex is 2, 19. All right, in this next problem, we're asked to find the y-intercept. So if you remember, to find your y-intercept, you can let x equal 0, and then just plug into the function y equals -3 times 0 squared plus 12 times 0 plus 7, which does just give you 7. Not C, 7. All right, so that's our y-intercept. To find the x-intercepts, you have to set the equation. You have to let y equal 0 and then solve it for x. So we're going to say 0 equals -3x squared plus 12x plus 7. So you could try to factor this, but it is not factorable, so we'll actually have to use the quadratic formula here. So we have the opposite of b plus or minus the square root of b squared minus 4 times a times c. And then that is all divided by 2a, which is negative 3. Okay, so if you start simplifying this, then you get negative 12 plus or minus the square root. 12 squared is 144, and negative 4 times negative 2 times 7 is positive 84. And then that's all divided by negative 6. All right, so this ends up being negative 12 plus or minus the square root of 228, all divided by negative 6. And the square root of 228 is about 15.1. So if I do negative 12 plus 15.1 divided by negative 6, you're going to get approximately negative 0.52. So that's one of your x-intercepts. And then if you do negative 12 minus 15.1 divided by negative 6, that's going to give you approximately 4.52. Okay, so those are your two x-intercepts. All right, let's look at domain and range. Oh, before that, we're actually asked to graph the function. So in this one, I mean, our vertex is pretty big, so we'll probably have to use a scale of something bigger than 1. I'm going to go ahead and use a scale of 3. So I'm going to say this is 3, 6, 9, 12, 15, and 18. So my x-intercepts, I can graph those first. Those are what I just found. So here's about negative 0.52, and then 4.52 is going to be about there. All right, and then my vertex is 2, 19, so I'm going to go over 2 up to 19. There's that vertex. And then remember our y-intercept was 7, so that's about here. And then I'm going to use symmetry to reflect that point over to here so I can get a better idea of what this graph is going to look like. So you notice it is this upside down parabola and that makes sense because notice your a value is negative, so you should expect a parabola that opens upside down. So what is the domain and range? Domain for any quadratic equation is just going to be all real numbers. The range is based on that vertex. So notice my vertex had a y value of 19, which means my range is y has to be less than or equal to 19 because it's never going to be above that vertex. All right. So we're going to move on to combining functions. In 2a, we're going to subtract this function f minus this function g. So this is just going to equal 7x squared minus 6. And here's where you have to be careful. When you're subtracting a function, put it in parentheses so you remember that you're subtracting the whole thing. So that negative is actually going to distribute into these two terms. And it's going to be 7x squared minus 6 minus 3x squared, and then it's going to turn into plus 5. So then when you combine like terms, 4x squared minus 3x squared, or 7x squared minus 3x squared is 4x squared, negative 6 plus 5 is minus 1. And then that there is your answer. All right, f times g is going to be that first function, 7x squared minus 6 times 3x squared minus 5. So this is actually going to end up being a foiling problem. 7x squared times 3x squared is 21x to the 4th. 7x squared times negative 5 is minus 35x squared. Then I have negative 6 times 3x squared is minus 18x squared. And then negative 6 times negative 5 is plus 30. So if we combine like terms, negative 35 minus 18 gives you negative 53 x squared plus 30. So then this would be the function f times g. All right, we're going to do a couple other things. With number 3, we're going to put f over g, and then we're going to find the domain. So we're working with a couple of different functions. F is x squared plus 10x plus 21, and we're just going to put that over x plus 3. Now, I noticed that first function, f, is actually factorable. So if you think of two numbers that multiply to 21 and add up to 10, that gives you x plus 3 and x plus 7. And then you still have the x plus 3 in the bottom. And in this case, these x plus 3's cancel, and you're just left with x plus 7 as your answer. So now, when you look at the domain, that's actually based on before you canceled. So you actually can't have x equal to 3, or negative 3. And that's just based on before you canceled. Remember, there was an x plus 3 in the denominator. So you still have to take that into consideration even though they canceled, just because g is technically still in the denominator. All right. So moving on, we are going to look at a rancher has 1,700 feet of fence to enclose a rectangular field, as well as divide the rectangular field into 5 smaller sections shown. So part A of this problem wants us to find a function that models the area of the enclosed rectangular field A in terms of the shorter dimension W. So for now, we're going to have to add in this length. And then notice we have 1, 2, 3, 4, 5, and then 6 W's here. So if you add up, and then you have L down here, if you add up all of those dimensions, that's got to give you that 1,700 feet of fencing. And you have 6 W's plus those 2 L's. But what we're going to do is solve this for L so that we can just have W in our equation. So I'm going to get rid of that 6W. So we have 1,700 minus 6W equals 2L. And if you divide by 2, we end up with 850 minus 3W is the length. Okay, so now I know area is length times width, but for length, I'm going to use this, not L. So my area is going to equal 850 minus 3W times W, which is just length times width. And then if we distribute that W and rearrange so it's in standard form, we have negative 3W squared plus 850W. So this would be the equation that models the area in terms of the width. All right. And in part B, it says determine the dimensions for the largest area of the field. So remember, whenever you see that word largest, you're going to think vertex. So to find the W coordinate, we're going to take the opposite of B divided by 2A. So in our equation, B is 850, so we'll have negative 850 divided by 2 times negative 3. And that's going to give you actually a fraction or decimal. It doesn't end up being a perfect integer, so you get 141.66666, so I'm just going to say 0.67 feet. All right, so now that we have the width, remember to find our length, we can just plug into this 850 minus 3w, and for w, we're going to use that 141.67. And if you do that, you end up with 425 feet. So your dimensions are the length by width would be 425 feet by 141.67 feet. Okay, so let's move on to what is that maximum area? Well, if you remember from a little bit above, we said area is length times width, and now we know our length is 425. We know our width is 141.67. So if we multiply those dimensions together, you get 60,209.75 square feet. All right, so that would be your area. All right, this next problem is kind of similar. So you have a property owner wants to fence a garden plot adjacent to a road as shown in the figure. The fencing next to the road must be sturdier and costs $5 per foot, and the other fencing costs just $3 per foot. The garden is to have an area of 1,200 square feet. Okay, so first thing I'm going to do is use that area part of this. And I'm going to say, okay, these longer dimensions are X, and then these shorter ones I'm just going to call L. So if we think of the area equaling the length times the width, and this problem is going to be 1,200 equals L times X. All right, well, why did I do this? I did this so that I can solve it for L and get that length in terms of X. So now for L, I'm going to use 1,200 over X instead of L, so that I just have that one variable. Okay, so now our cost, remember this part here next to the road, they want sturdier fencing, which costs $5 per foot. So if I take $5 times the number of feet, that's going to give me that part of the fence next to the road. The other pieces are only $3 per foot. So I'm going to add on this top one is just going to be $3 times the number of feet. This side one is going to be $3 times the number of feet, which we'll use 1,200 over X. And then this other side over here is going to be another $3 times 1,200 over X. So at this point, we're just going to start simplifying. I have 5x plus 3x is 8x plus, and then this, if I multiplied 3 times 1,200, that's 3,600 over x. Same thing here, 3,600 over x. So the cost is going to be 8x plus 7,200 over x. All right, so that is our cost formula. All right, part B then says find the garden dimensions that minimize the cost of fencing. So we're again, if you're looking at the minimizing, you're finding like a local minimum. Now this function is not a quadratic, so we're actually going to use Desmos to model this. So let me go ahead and open up Desmos here. Right. All right, so if we go to Desmos graphing calculator, and we're just going to plug in that function we came up with. Okay, so we'll say y equals 8x plus 7,200 divided by x. And we're going to zoom out quite a bit here. So this is kind of an odd looking function. It's a reciprocal function, so it's got that kind of weird branches going on. We don't really care about this point because we know that we're dealing with area and dimensions, so we can't have a negative dimension, okay? So we're going to use this value here, 30 comma 480. So that point is like our x and our y. So what was that? It's like 30, 480. All right, so 30 comma 480, that's that local min. So what that means, okay, so x is 30, and then our cost would be 480 because that's our y value in this equation. So we want the dimensions, so I'm going to go back up to this part to get the length. So my length is going to equal 1200 divided by x, which 1200 divided by 30 will give you 40. Okay, so now we know our dimensions are going to be 40 feet by the 30 feet, which will be like the dimension by the road. So that, if you use those dimensions, you'll get that 1200 square feet of area with the lowest cost. All right, let's move on to the next page. So we're gonna look at composition now. In part 6a, we're gonna start here. We're gonna find g of -3. So we're gonna start with that g function. Plug -3 in for x. So -15 plus 2 is -13. Then we're going to take -13 and plug it into the f function. So we found g of -3 and found that it was -13. So then f of -13 is 2 times -13 squared plus 1. So that's 2 times 169 plus 1, which that ends up giving you 339 for your final answer. All right, this next one is pretty similar. We're going to start by just rewriting this. This is actually g of f of 5. So the first thing we need to do is find f of 5. So f of 5 is 2 times 5 squared plus 1. So 5 squared is 25. 2 times 25 would give you 50. So you end up with 51. All right, so now that we have that, we're going to find f of, or g of 51. So we found f of 5. We found that that's 51. So now we're going to take g of 51, which is 5 times 51 plus 2, which is 255 plus 2, which gives you 257. So that's going to be your final answer. All right, the last one here, we're actually going to get a function for our answer. So we're going to take this g function and place it in for x in the f function. That's going to give us 2, and then in parentheses, we're going to have 5x plus 2 squared plus 1. So you are going to actually have to FOIL this. So this gives you 2 times 5x plus 2 twice. So that part will need to be FOILed, plus 1. So if you FOIL that out, you get 5x times 5x is 25x squared. And then you'd have 10x plus 10x, so that's 20x. And 2 times 2 is going to be plus 4. All right, then if we distribute that 2 into the parentheses, we have 50x squared plus 40x plus 8, and then at the end we have plus 1. So then if we add those constants, we get 50x squared plus 40x plus 9. So that would be your final answer. All right, in number 7, we're going to work with 3 functions. So 7a, we're going to start from the inside and work our way out. So h of 5 is first. H of 5 is going to be 5 squared plus 3. So I'm using the h function. So 25 plus 3 is going to give you 28. Now we're going to take 28 and put it in for the g function. So g of 28 is our next step. And that's just 28 divided by 4, which is equal to 7. And now we're going to take that and plug it in for f. So f of 7 is just going to be 7 minus 7, which is 0. So 0 is your final answer. Okay, and now in B, we're going to have a function for our answer. So let's start with this. Let's find g of h of x. So we're going to plug h of x in for x in this g function. So instead of having x over 4, we will have that entire function over 4. So we'll have x squared plus 3 all over 4. Now we're going to take that function and plug it in to this function for f. And that will give us f of g of h of x. All right, so instead of having x minus 7, we're going to have this entire function, x squared plus 3 over 4 minus 7. So for this problem, I'm going to put this 7 over 1, multiply these by 4 to get a common denominator. So I have x squared plus 3. Negative 7 times 4 is negative 28. And now that's all over 4. And then I can combine the 3 and the minus 28 to give me x squared minus 25 all over 4. So that just makes it look a little bit neater. All right, now let's use some graphs to evaluate functions. So in part A here, f of 0 just means you're going to go to 0 and see that f has a y value of 2 plus g of negative 2. So if we go over to negative 2 and go down, g has a value of about negative 1. So then 2 plus negative 1 would give us an answer of 1. All right, in part B, we're going to find g of f of 4. So just like before, we're going to start from the inside out. We're going to go to f of 4, which is right here, and that has a value of 0. So now we're going to find g of 0. So now we go to our g function, go to 0, and I go down, and that has a value of about, so I'm going to change this to approximately equal to, it's not exactly, and I'm going to say negative 1.2. All right, part C, if you remember, you can write this as f of negative 2. So we're still going to start from the inside out, finding f of negative 2 first. So f of negative 2 means we're going to go to negative 2, and we're going to go to f, and that looks like it has a value of 1. So this equals f of 1. And now we go to 1 and we go up, and that looks like it has a y value of about 2.4. All right, and then in this third part, we are going to find all local extrema. So that's like just a fancy word to say like local maxes and mins. So I'm going to find my first local extrema. So I can see this one here is a local max of, and we look at our y value, I would say it's about 2.2. And that is at x equals negative 1. So So that's referring to this point right here. All right, now our local min is next. That's like a low point. So we have a local min of 2 at x equals 0. And then the next one would be about here. I would say it's a y value of about 2.8. And that's a high point, so I'm going to say it's a local max of 2.8 at x equals 2. So those are all your local extrema of that function f. All right, and in number 9, we have these graphs given, and we're going to answer which ones are functions and then which ones are one-to-one functions. So for that first part of the question, which ones are functions, we have to see if it passes the vertical line test. So I notice if I draw a vertical line through this graph, this is not a function because it passes through twice. So this is not a function, and it's because it fails the vertical line test. So the vertical line test can tell you if something is a function or not. So I don't even really need to answer this second question because if it's not a function, it's obviously not a one-to-one function either. Okay, let's look at this next one. So this, notice these vertical lines are all passing through just once. So it is a function. And that's because it passes the vertical line test. That was something from a couple units ago. We talked about that. But now, is it a one-to-one function? Well, now we're going to do what we call the horizontal line test, which you can see that is passing through multiple times, 3 times in some places. So that we would say this is not one-to-one, and that's because it fails the horizontal line test. So a horizontal line test, if a horizontal line passes through the function just once, then we say it's a one-to-one function. All right, in our next one, I am noticing that this is not passing the vertical line test. So it's not a function. And if it's not a function, and you don't even have to have, there's no debate whether it's one-to-one function because it's not a function in the first place. And that, again, is because it fails the vertical line test. Okay, this fourth one is passing the vertical line test, so it is a function. And that is because it passes the vertical line test. So now let's check our horizontal lines. It's also only going through these horizontal lines once. So it is one-to-one, and that's because it also passes the horizontal line test. All right. Okay, so now we're going to look at some graphs, and we will graph the inverse function. So for number 10, to start out here, we're going to make a table of x, y values. So I'm just going to pick a few values on this graph to use. So way over on the left here, if I have a x value of -4, I have a y value of 3. If I have an x value of -2, I have a y value of 2. This y-intercept is 0, 1. Then I have this x-intercept of 2, 0. And then this point way on the right is 4, -1. So we know inverse functions just switch x's and y's. So now my x values are going to become 3, 2, 1, 0, -1. And my x values are going to become -4, -2, 0, 2, and 4. So these just swapped places, and now we're going to graph those points. So 3 comma negative 4 is this point down here. 2 comma negative 2 is here. 1 comma 0 is here. 0 comma 2 is here. And negative 1 comma 4 is here. So this line right here would be the inverse of that line that was graphed. And notice if I graph in this line y equals x, remember those should be a reflection over that line if they're inverses of each other. So that's a quick way that you can check. Okay, in this next one, this one, notice like if I draw in a horizontal line, it's not going through once, it's going through twice. So I don't even really need to answer this question. I should still write an explanation. So this is not a one-to-one function. So it doesn't have an inverse. So if it's not one-to-one, you can't even talk about inverses because only one-to-one functions have inverses. So that one, we actually can't graph its inverse. It doesn't have one. All right, looking at number 11 then, we're given two functions. We're given function f and function g, and we're going to show evidence to determine whether or not functions f and g are inverses of each other. And then we're going to explain our answer. So we can show this using composition. So first I'm going to find f of g of x. So I'm going to take that g function and plug it in for x in the f function. So this is going to be 2x minus 6 over 2 plus 6. All right, so if I simplify this, look at these 2's cancel. And then we just have x minus 6 plus 6. These 6's also cancel, so we're just left with x. All right, now we're going to go the other way. We're going to take this f function and plug it in for x in the g function. So in other words, we're going to find g of f of x. So instead of having x minus 6 all over 2, we're going to have 2x plus 6 minus 6 all over 2. So these 6's cancel, and we're left with 2x all over 2. And your 2's cancel, so now we just have x. So that's showing us that these two functions are inverses of each other. So you know they're inverses because you have f of g of x is equal to x, and g of f of x is equal to x. And that means f and g are inverses of each other. So when you do the composition both ways, you have to get them both to equal x. All right, so this is our answer with our explanation. Okay, all right, and then in 12, we're actually going to find the inverse. So we're just given a function. The first step is to write it as y equals, and then the second step is to switch x and y. And now we're going to solve this for y. So I'm going to subtract 1. So these cancel. And then I'm going to say x minus 1 is equal to 2/3 y. And then I can multiply by the reciprocal. To get rid of that 2/3, I'm going to multiply by 3 over 2. So those cancel. And then I'm going to distribute and say, okay, we have 3 over 2x minus 3 over 2 is equal to y. And then we'll just write that as f inverse of x is equal to 3/2 x minus 3/2. So that would be your inverse function. All right, in part B, same thing. We're going to start with y equals negative 2x to the 5th minus 7. Then we'll switch our x and y. And now we'll solve for y. So I'm going to start by adding 7. Get x plus 7 equals negative 2y to the 5th. And if we divide by negative 2, these cancel. So we have x plus 7 all over negative 2 equals y to the 5th. And then we'll take the 5th root. So I'm just going to leave my answer as a big fraction and say f inverse of x is equal to the 5th root of x plus 7 all over negative 2. All right. Okay, so we're going to move on to some word problems for the rest of this review. In number 13, they want us to find a function that models the area of an isosceles right triangle in terms of the length of one of its legs, L. An isosceles right triangle is a right triangle that has both of these legs equal to each other. So if this is L, this is L. And we're talking about area here. An area of any triangle is 1/2 base times height. So in an isosceles right triangle, your base is the L, your height is the L, so your area is just 1/2 L squared. So that would be the area of the isosceles right triangle in terms of one of its legs. All right, number 14 has to do with a right triangle as well, but this one's a little different. So it says a right triangle has one leg that is twice as long as the other. Find the function that models its perimeter in terms of the length x of the shorter leg. So if we draw this right triangle here, where this shorter leg is x and this other leg is twice as long, well, that's going to be 2x. And for now, I'm just going to call this hypotenuse C. Since this is a right triangle, we can use a squared plus b squared equals c squared. And our legs are a and b, so I'll say x squared plus 2x squared equals c squared. Or x squared plus, you have to sprinkle this in and get 4x squared. And that's actually 5x squared altogether, which equals c squared. And then we're trying to get c in terms of x. So if you square root this, you can actually square root both pieces separately. And this just becomes root 5 times the square root of x, which is just x. So that's c. So now my c is just x times the square root of 5. All right, now to find perimeter, we're just going to add up all three sides. So I have this side here of x plus this side of 2x plus this hypotenuse, which is x root 5. And then I'm just going to go ahead and combine my like terms x and 2x. So the perimeter in terms of x is just 3x plus x times the square root of 5. All right, in 13, you have the volume of a cone is 100 inches squared. Find a function that models the height h of the cone in terms of the radius r. So we're going to start with this cone. And that wasn't a great job there. And we have this radius is what we want to write everything in terms of. And we have this height, h. So we're going to start with the volume formula of a cone, which is 1/3 pi r squared times the height. And we know the volume is 100 inches, and this should actually be cubed. This volume is cubic units. So if we start with filling that in, we have 100 equals 1/3 pi r squared times the height. And we want to find a function that models the height in terms of the radius, which that is a fancy way of saying solve for h. I'm going to start by multiplying both sides by 3 to get rid of this 1/3. Now I have 300 equals pi r squared times the height. And now I just have to get rid of everything except for h, so I can do that by dividing by pi r squared. So that these pieces cancel. And now I have my height in terms of the radius is 300 divided by pi r squared. All right. In number 16, this is a problem where we're going to try to find the income. So it says you run a canoe rental business on the Kickapoo River. You currently charge $18 per canoe and average 40 rentals per day. A market research study suggests that for every $1 you reduce the rental price, you will gain 4 more rentals. Find a function that models income in terms of price. So we know that to get the income, we have to take the rental price and multiply that by the number of rentals. So like right now you would multiply your $18 times 40, and that would tell you how much money you would make, or how much income you would get. So the rental price, we're actually just going to call that X. So that's going to be our variable. Now to figure out this part, the number of rentals, that's kind of the tricky part. So we know we already have 40 rentals. And this part here is telling us, okay, so every $1 you reduce the rental price, you're going to get 4 more rentals. So let's say like you reduce the price to $16. Well, then you would have 8 more people going, right? So what you're doing there is you're saying, okay, I'm going to take 18 minus my new price. So like say it was 16. 18 minus 16 is 2. And then you take that 2 and multiply it by 4 to get the 8. And you could do that with any number. You could plug 17 in for this price. And then 18 minus 17 will give you 1. 1 times 4 is 4. 4 more people will rent canoes. So that is going to give us the number of rentals, but we can simplify this. So if we distribute that, we get 40 plus 72 minus 4x, which gives you 112 minus 4x. So this is the number of rentals right here. So now we're going to go back to this income function. We have x, which is the rental price, times 112 minus 4x. And if we distribute that x and then rearrange this, we get our function negative 4x squared plus 112x. Now suppose this problem said like find the maximum income. We know that if we were going to find that max income, I know it doesn't say this, but maybe it will on the test. So the max income is just going to be finding your vertex. So like this is your A. Oh, I missed an X here. This is your B. So we would take the opposite of B over 2A. So that'd be negative 112 divided by 2 times negative 4. You'd have 112 divided by 8. And whatever that is would give you what you should lower the price to. So if we take 112 and divide it by 8, we get 14. So that tells you if you lowered the price to $14, you'd get that max income, and then you could take that, plug it in for x in that equation, you'd get negative 4 times 14 squared plus 112 times 14. And if you plug that in, you end up with $784. So I know that wasn't part of the question, but if it did ask that, you would charge $14 per the tickets and you would make $784. All right. So in this next one, we have a manufacturer makes a metal can that holds 1 liter of oil. What radius maximizes the amount of metal in the can? We'll start this one. Actually, I don't expect you to like memorize this, but 1 liter, we're going to use actually 1,000 cubic centimeters. It just makes the math work out a little better. So we're going to start with the fact that the volume of a cylinder is pi r squared times the height. So we have 1,000 cubic centimeters for our volume. And then since we only want radius as our variable, we're going to solve this for h. So I'm going to divide by pi r squared. And then these will cancel. So our height is 1,000 divided by pi r squared. So now we have to look at, okay, what radius minimizes the amount of metal? That's actually going to be asking for the surface area in terms of the radius. So surface area for a cylinder is 2 pi r times height plus 2 pi times the radius squared. But for this height, we're going to replace it with this right here. So if we do that, our surface area in terms of the radius is 2 pi r times 1,000 over pi r squared. And this second term is going to stay the same. So we can simplify this a little bit. This pi cancels this pi. This r cancels this square. So then your surface area in terms of the radius is 2 times 1,000. We can just write it as 2,000 over r plus 2 pi r squared. Okay, so that's the formula. Now we have to figure out what radius minimizes the amount of metal. Well, this is not really a nice equation. The only time I'll make you do this by hand is if it's a quadratic. So if it's like an x squared or r squared or something. So to answer this question, we're actually going to use Desmos because this is not a nice one to do by hand. So if we go over back to Desmos here, we're going to plug in that function, which is, let's see, 2,000 divided by r. So I'm just going to use x for that. And then we have plus 2 pi x squared. So this is kind of a strange looking function. You can see it's like kind of this wiggly looking thing going on. And I don't really care about any of these negative values because we can't have a negative radius. So this point right here is actually the point that we're interested in, this local min right here. And what that is telling us is that if you have a radius of 5.42, you're going to get a surface area, which is the minimum, of 553.58 centimeters squared. So that point is the one that we are interested in. And we're actually, since it's just in our problem asking for the radius, we just really want that x value of 5.42 centimeters. And that y value would tell you like that would be the the amount of metal in squared centimeters. All right. 18 is one we will be able to do by hand. We've done a few problems like this in class. So it says, among all rectangles that have a perimeter of 34 feet, find the dimensions of the one with the largest area. So here's this rectangle, and we know that this is X, and I'm going to call this L and this L. Doesn't really matter what you use for those dimensions. But I know for my rectangle, the perimeter is going to be 34, which it has to come from those two X's plus those two L's. All right, and I want to solve this for one of the variables. I'm going to solve it for L so that I just have X in my final equation. All right, so these cancel. We get 34 minus 2X equals 2L. And if we divide everything by 2, we get 17 minus X is the length. So now if we think of area as your length times your width, well, for length I'm going to use this, and for width I'm going to use X. So I have X times 17 minus X. If we distribute and rearrange this, we'll get the area is negative X squared plus 17X. So now I want to find the dimensions with the largest area. So we're finding the vertex. To get the X coordinate, we take negative B and divide it by 2A, which is negative 17 divided by 2 times negative 1, which is positive 8.5. And then to get your Y coordinate, we can go back over here. So that's going to give us our length is 17 minus 8.5, which is also 8.5. So the dimensions with the largest area would be 8.5 feet by 8.5 feet. And if you didn't know, that's a square, which always would give you the biggest area. All right, 19 is a little bit trickier. So in 19, we have a box with an open top is to be constructed from a rectangular piece of cardboard with dimensions 12 inches by 20 inches. So they have this 12-inch by 20-inch piece of cardboard, and then they're just going to cut out these squares on each corner so that they can fold up and make this box here. All right, so that's kind of the idea. And what we want to do first is find a function that models the volume of this box right here in terms of just X. So here's how I'm thinking of this. This side here is found by taking this 12 inches. So this matches with this right here. That side is that side. So that side is not 12. That side is actually 12 minus these two X's here and here. Okay, it's kind of tricky, but that is that dimension. This side right here, so this longer piece here, that side goes with this, and that's not 20. That's 20 minus this X here and this X here, which is 2 X's. So now we have like the 3 dimensions we can multiply together to get the volume. So the volume of this box is those 3 pieces multiplied together. So X is our height times this 12 minus 2X is our width times the 20 minus 2X is your length. So the volume is going to be given by this. So now we're going to have to FOIL this back part. So this X I'm going to leave alone for now. 12 times 20 is 240 minus 24X minus 40x plus 4x squared. All right, so this is volume is x times 240 minus 64x plus 4x squared. So our volume in terms of x, the last thing I'm going to do is distribute that x and then rearrange. So I get 4x cubed minus 64x squared plus 240x. So that would be the volume in terms of that dimension x. All right, so then B says, for what values of x, find the values of x for which the volume is greater than 200 cubic inches. For this one, we're trying to see like, okay, when is this function greater than 200? So for this, we will also use Desmos, because this, I wouldn't expect you to do that algebraically. Try to solve that would be pretty tricky. So if we go to Desmos, X this out, and we're going to type in that function we just came up with. So we have y equals 4x cubed, and then it was minus 64x squared plus 240x. All right, so let's zoom to where this makes sense. So it's kind of got this snake motion going on, but it's very steep because those numbers are so big. But I'm also going to add in this function y equals 200 so I can kind of see what's going on here. So if we go to 200, so this function right here, the blue is our actual function, and this line is just going to help us see this intersection. So this point right here is showing me that at an x value, in other words, at that x dimension, you have a volume of 200. And then you also have the same thing happening here. You can't really consider this like other part here. That's not really useful because that branch is like going below 0 and then coming back up. So you're really only looking at these two values, those first two intercepts. So here and here. So those are the x values that you could be between that 1.174 and 3.898 in order to be greater than 200. Because notice like all these x values here are bigger than 200. They're giving you a y value bigger than 200, and it keeps going until you get to that point right there. So those are x values that you can use. 1.174, and then it could go up until that other one was 3.898. And then those would be in inches. So it could go from 1.174 inches to 3.893 inches, and then that would give you a volume bigger than 200. All right, and then in part C, it says find the largest possible volume for this box. So again, for this one, we'll use Desmos because again, that would be tricky to find the vertex for that. I mean, it doesn't really have a vertex because it's not a quadratic. So if we go back to that graph, I'm going to get rid of this function now. If we go up to this tippy top right here, that is going to be your max volume, and that is happening at 2.472 or 2.427 inches. So that point there is like your local maximum. So I would say you have a max volume of, let's see, what was that y value? 262.682. And that would be inches cubed at an x value of 2.427 inches. All right, so that would be your max. All right, lastly, we have a problem similar to that one. An open box with a square base is to have a volume of 12 feet cubed. Part A says find a function that models that surface area of the box. So if we start with just drawing a quick sketch, we have this box here with an open top. So this part up here is open. And it has a square base, so I know this is x by x, and I don't know what the height is. But I can start with the fact that the volume is found by multiplying all three dimensions together, and I know that volume is 12 feet cubed. So I'm going to solve this for h to get that in terms of x. So these cancel. And now I have 12 divided by x squared is my height. So now I can figure out my surface area in terms of x because I have those dimensions all in terms of x. So the surface area in terms of x. So if I think of this bottom part here, that's just an x by x square. And I only have the bottom because this top is open. So that's the bottom. And then I have these four sides. If you think of this as being one side and then the front as being side 2 and then this side on the right and then the back. You have four sides that are x by h. But we're not going to use h, we're going to use this. Okay, so my surface area in terms of x is x squared plus 4x times 12 divided by x squared. All right, and then we're just going to simplify a little bit. So we have x squared plus 4 times 12 is 48. And then what happens is this x cancels this square. So then it's just 48 over x. So then that would be your surface area in terms of x. All right, and then notice again, this is not a quadratic because you have this x in the denominator. So in order to find the box dimensions that minimize the amount of material used, you guessed it one last time, we're going to use Desmos to find that value. So if we plug that in, see what this looks like. We have y equals x squared plus 48 divided by x. So we'll try to see where this does what we want. So notice like this part over on the left is like weird and we wouldn't even worry about that because you can't have negative dimensions. So we want to minimize the amount of material. So we're looking at this local min right here. So that means at a y value or at an x value of 2.884, you would use 2.4961 square inch or square feet of material. So that point tells us that local min that we found, which was 2.884 comma 24.961, that was the lowest surface area at that x value. So we found our x, but we also want to find our height, which we can go back over here and plug in 12 divided by 2.884 squared. And that would give you a height of about 1.44. So I'm just going to say our dimensions are, the x by x base would be about like 2.88 feet by 2.88 feet by that height of 1.44 feet. So those dimensions would give you the lowest surface area. All right, I hope that helped. If you have any questions, you can comment below or come see me in class or during office hours. All right, have a great day. Take care.